All right, everybody, welcome back. Today we are going to be discussing functions and their graphs. One thing I do want to point out to you right away is we are starting on slide number 33 of your note packet. So that's going to look a little bit different than what you probably would have had next in order. Our objective today is that you will recall relations, functions, domain and range, and one-to-one functions. You'll also be able to identify the domain and range of graphed equations. Now, today really has a lot of different pieces that are all going to come together, and they're really big pieces. So it's important to sit there and make sure you're asking questions as you're coming up to stuff. So I would just remind you to jot down any questions that you have so that we can make sure that next time we're together or even outside of class so we can have those conversations. The first part of today is just going to talk about a concept that's relatively basic. Functions that are either increasing, decreasing, or constant. So couple of ways I like to think about this, but the first one is that anytime I'm trying to determine if a function is increasing, decreasing, or constant, I always need to look at that graph from left to right. Just like you read a book, you are going to read a graph the same way. If from left to right you see that your graph goes up, we can say that our graph is increasing. If we see that our graph goes down, our graph would be said to be decreasing. And finally, if we see that our graph stays the same, we say that our graph is constant. So those are really our three different types. So we have increasing, constant, and decreasing, and all of them are based on our graph going from left to right. So for graph A here, if I start on the left and I go to the right, I see that I slowly move uphill, which means this one is increasing. For graph B, if I start on the left and I work downhill, we would say that our graph is decreasing. And finally, for graph C, I start on the left and I stay the same all the way. My y value does not change, which means that our graph is constant. Now, in these three graphs that you've seen here, you've only seen, or throughout the entire graph, it was either increasing, constant, or decreasing. It never changed in the middle, and that's kind of abnormal for the graphs that we're going to be looking at. So we'll see some changes, and you're going to see graphs that are going to have sections of increasing, sections of decreasing, and even sections of constant. Next big idea that we're going to talk about is the idea of what we call a relative minimum and a relative maximum. Now, what a relative maximum and minimum are is they're essentially saying that they are either high points or low points on your graph. That did not end up as a circle. Let's try again. So there's my circle, right? So normally when you do this, I like to think about it as if I just put a circle over it, right? And if you zoom in really close to that point, you will see that this is essentially a high point, right? You rise all the way up and you get to this spot that we call a high point. Now, this is what we would call a relative maximum. And the reason we call it a relative maximum is because at this point, it absolutely looks like a maximum for our function. Now, similarly speaking, if I zoom in really close over here, right, it appears that my function kind of bottoms out and that this would be the bottom of the function. So again, we call this a relative minimum because we have this low point. Now, one thing that we can see here, though, is that our graph actually continues up, both up and down. Our graph does continue to get higher and higher and higher, and lower and lower and lower. So really looking at that thing, we can see that neither one of these is truly a maximum in terms of the whole graph or a minimum in terms of the whole graph, because there's going to be a lot of points that get lower, but they are relative maxes. So what a relative max is compared to everything else around it. If you zoom in really close, it looks like we get a high point, right? So that's a maximum that's relative to everything that's kind of around it. Similarly with a relative minimum. If you have a point on your graph where it is like the low point, if you were to zoom in really closely, and you see I'm zooming in really close here, where I'm not seeing those other parts of my graph, that's enough for us to say that this is a relative minimum. It's a minimum compared to everything else that is around it. Now, one thing to know about this that is important is that when we write these, we are going to write these as ordered pairs, okay? So we'll practice all of this stuff and pull it all together at the end of the lesson. but these will always be written as ordered pairs when we have them. It does say, note, there can be more than one relative maximum and more than one relative minimum. And if we come over here and we put our little circle on, right, and we zoom in and we're only thinking about that function in that circle there, it does look like that red dot is actually a high point for us, which means it will be a relative max. Now, similarly speaking, over here we will have another high point, right? If I zoom in and this was all I can see that my function goes up, 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 and then it stops, and then it starts to go down, 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 right? We did have that high point, that was our maximum. And then actually on the same graph, we can see down here that this would actually be a relative minimum because it's a low point for our function there, relative to the rest of the graph around it. And similarly, we would have another relative minimum over here. Now, it's important that for something to be a relative max or a relative min, it's just compared to what is around it. Now, one unique situation that I don't think we see here but will come up later on is actually if our graph were to have ended here. So if this graph would have ended, and instead we would have just had an endpoint right here, right? So now we don't have the arrow that continues on forever. This actually would also be considered a relative minimum because that would be the lowest point on our graph compared to everything else around it, right? This is definitely lower than all of this other stuff that's happening right here when I zoom in really close. This is the lowest point according to that. So if this were to be the case, we could also call this a relative minimum. It's not a relative minimum when it has the arrow, but if it were to have been an endpoint, you could also have looked at it that way too. Now, it does say, note, there is not always a relative maximum and a relative minimum. Functions don't need to have these two things. So if I look at this first graph that we can see kind of keeps going here, and I just pull up my circle again, it's the easiest way for me to kind of just try to show you what's going on. Right here, we can see that our graph really never stops, right? It goes up, and then it goes up, and it kind of flattens out, and then it actually kind of keeps going up. It never actually changed to be this high point. Really, to have a high point, your function needs to be going up, and then it needs to flip to going down, right? It needs to be switched from increasing to decreasing, really, to get that high point or low point. Similarly, moving my graph over here a little bit, the same thing kind of continues to happen, right? Our increasing is just really faint right now, but we are going up, 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 and then we kind of take off like a rocket. But we never had that spot where we were really switching from increasing to decreasing. Looking over here at this other graph, so a couple different points here, right? So we're always looking at our turning points. Right here, this would not be a relative max. And the reason for that is because, yes, it does look like a max coming in from this side, like we're getting to a high point here, but over here, this is staying constant here. So all of these are just points. Now, in order for something to be a relative max, is that when you zoom in really close on that spot, that is the high point. And in this situation, this point would not be the high point because right next to it, we have a point that is equally as high. And to be a relative maximum, it strictly is the highest point. And since you would have two that are really at the same height, that would not constitute. Looking at the rest of this graph, in the middle here, we just kind of have a little bend in our graph, but it's not like we have a high point right there because we can see points that are higher than it right around it. And then moving down to this last part, this is going to be similar to the first one. Coming in from the left here, it looks like this could potentially be a min, but then we start to notice that it just flattens out. So this point is as low as any of these other points that are over here on this line. So that would not be the lowest point in that region, so it's not a relative minimum. So again, you don't always need to have a relative maximum or a relative minimum, but they are different things that we will be looking for and pointing out on our graph. Now, looking at this graph, right? So this graph is going to have multiple relative maxes and relative minimums. So looking at this, we see that we would have a relative min right here. So again, our graph is really switching from decreasing to increasing at this point. Our graph's going down, 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 and then we get the switch, right? So down, 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 and then there's our switch where now we're going up, up, up. That's really that piece that's indicative of having a relative min or a relative max, is that we see that our graph really switches from increasing to decreasing. Now, if I just move my circle up here, again, as our function continues on, we're going to be increasing, 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 and then we flip and go to decreasing. When you get that flip, that means there is a highest point that occurs here, and that point would be considered our relative maximum. Moving along on our graph, we'll see this repeat a couple more times. We'll see another relative minimum right there. We'll see another relative maximum right here. And finally, we will see a last relative minimum over here. Now, since our graph, it's hard to see, but it looks like someone did try to show us that this thing continues forever here. Since our graph does keep going up and up and up, those two, or those endpoints, do not get considered to be relative maxes at all. So, at this point, we have, it looks like 5 different things that we'll be listing. So for our relative maxes, again, we list these as points. So for our first relative max here, it looks like it was at -2, +2. And then it looks like we had another relative max at 2, 2. Now going through and looking at our relative minimums, we had a relative minimum happening here. And I know our graph doesn't quite hit it, but I think that's really what we were trying to show when whoever made this. So let's just say this is at -5, -5. Up here, you would hit 0, 0. And finally, over here, we would hit 5, -5. Now, it does say, it gives us kind of a question in here. It says, why are these maximums and minimums called relative or local? And really the reason for that is because they are actual true maxes and minimums if you look at the stuff that is only close to it, right? What is really close to those points, that would be the high point or the low point, right? So that's really why we get this name of relative or local. It's what's close to you that we are comparing it to. Compared to everything that's around you, you are the high point. Compared to everything around you, you are the low point, right? Now, here's another one. So it says, find where the graph is increasing and where it is decreasing and where it is constant. So looking at this graph, a couple things you'll notice. So again, right down here, you'll see your relative minimum, right? This would be that relative min. Now, easy way to sit there and to start talking about increasing and decreasing is actually to find and identify any relative mins or maximums and to strictly come over there and just to kind of draw a light line through there. Now, the reason we do that is because if you have a true relative minimum or maximum, that's really where you're going to switch from increasing to decreasing or from decreasing to increasing. So for this graph, we see that we are coming down, 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 till I get to that point, and that's where I really flip and I start to go up, 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 right? So now I can see my graph going up, up, up. So in this situation, we were really decreasing, right? So decreasing, going downwards from -infinity to a +2, right? And we're talking about our x values. We're decreasing when x is -infinity all the way to -2, and then at -2 we can see that that kind of stops. Now for increasing, our y values were increasing when x was from 2 all the way to infinity, right? So we're going up as our x values move out this way. In this particular situation, our graph was never constant. It never was flat where it wasn't changing, so we would just say nope, or none, or nada, or nilch, whatever you want. Let's look at another one. So I guess we got some steps here. It says how to determine where a function is increasing or decreasing. It says first, determine the relative inflection points. Those are going to be those maxes and mins. Once you have those, we're going to draw the light lines, and then we are going to write an interval notation. Moving on over here, so looking at this part right here, it does say where is the function increasing, decreasing, and constant. So coming over here, again, what I would suggest is drawing a line through any relative mins or maxes you see. Now, officially, this is not a relative min or max, but this is a turning point that we want to kind of pay attention to. So looking at our graph, remember, increasing and decreasing are always determined from left to right. So from left to right, we can see that our graph rises on this interval. So this is where we are increasing. And then in between here and here is where our graph starts to decrease. It goes down. And then we increase again. And then finally, over this way, our graph just stays flat. So this is where we are constant. So in order to write these things out, we write them with intervals. So from negative infinity all the way over to, this looks like it's -3, this was 1, this was 3, and this was 4. So from negative infinity to -3, our graph was increasing. And then from -3 all the way to 1, right? So from 3 to 1, this section is where we were decreasing. And then we went back to increasing, so we were increasing again from 1 all the way to 4, right? From 1 to 4 on this little interval here, we were increasing. And then finally, from 4 to infinity, since it stays flat the rest of the way, our graph will be staying constant, right? And that's really why we look at the relative min and max first, is because those help us to determine where our graph is truly increasing or decreasing. Now, one last piece that hasn't been discussed yet, and I didn't have a slide in here for it, so I want to make sure you know about it, is symmetry. There's going to be two types of symmetry that we talk about. We talk about even symmetry and odd symmetry. Even symmetry is when our graph gets reflected about the x-axis, and it's symmetrical. So looking up here, this would be an example of a graph that would be symmetrical. If I flipped it across my y-axis here, it would land strictly on top of each other, right? If I folded that piece of paper there, it would land on top of each other. That's enough for us to say that this thing has even symmetry. This shouldn't say x, this should say y. Sorry, guys. Now, for odd symmetry is actually completely different than that. So odd symmetry is if it has rotational symmetry 180 degrees about the origin. So an example of that, I haven't seen one yet, might look like this. So if I get my graph, if something were to have odd symmetry, this would be an example of it. And what I mean by it is this: if I were to rotate, and when I think about this, I'm only really rotating this portion. If I rotate this around 180 degrees about the origin, this would land exactly on the other half of the function, right? So when I have something that has that 180 degree rotational symmetry, we could say that it is odd symmetry. The last part of it is neither. Not every graph is going to be symmetrical. So for example, for the one we just saw in this slide, this has no symmetry at all. There's no rotational symmetry where it would land exactly on it. There's no reflection across the y-axis that would make it land on it. So there is no symmetry happening here. This is really what your homework's going to look like down here, is where you're going to start to try to really tie all of these ideas together. Now, the first idea that we are going to try to tie together is domain and range. So remember, with domain and range, it's what x values does your function hit. It looks like our x values are always going to be falling from negative infinity all the way up to a +3. 3, right? Your domain or just your x values. For your range values, it looks like we hit y values from from positive 4 all the way to negative infinity. So again, we always list those from negative infinity, from least to greatest, all the way up to a positive 4. Right? And those would be our y values. Great. Nothing new there. We've been talking about domain and range for a while. Now we got to identify our relative maxes and our minimums. So looking at this thing, it looks like we have a relative maximum right here. That point is the point 1, 4. That was the high point in our graph. And it actually looks like we have a relative minimum too. Now, our relative minimum actually occurs right here. So zooming in on that point would be the low point. And we talked about this briefly when we changed the problem previously, where if you have it at that end point, that does still count. So we do have a relative minimum occurring at 3, 0. Now, as for our increasing, decreasing, right? So thinking about our graph, it appears that we are increasing all the way over here. We're going up, 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 up. We hit our high point, and then we drop a little bit. So then we decrease from there. So we are increasing from negative infinity all the way up to 1, right? Our increasing values, we always are just referring to our x. For our decreasing values, we start to decrease, or we see our function get lower on the y-axis from 1 to 3. Now, this graph did not have any flat points. There was no spot where it stayed constant, so we can say, nope. One piece we haven't talked about yet is the zeros. So zeros happen anytime your function crosses the x-axis. So we can see that happen right here and right here. Now, when you have those zeros, we write those at points. So we'll say this is negative 3, 0. And 3, 0. You have 2 zeros where it crossed. And last but not least, we need to talk about your symmetry. This one is not symmetrical about the y-axis, right? So it can't fold across there. That won't work. And it also does not have rotational symmetry, so we will say that this has none. Let's take a look at another one. All of these graphs kind of have their own little twist and turn that make this harder or easier. So here's our next one. It says find the following. Domain, range, you can see it all. So looking at our domain here, it looks like if all of this were to fall down, that there would be no points that got missed and that it keeps spreading out. So we'll say that our domain is all real numbers. If this all got pushed to the side, it looks like we do have a low point over here that would be at negative 4. So we would go from negative 4 all the way up to a positive infinity. That would be your range. So I would say my range will be from negative 4 to positive infinity. Now, in terms of a relative minimum or maximum, we do have a relative minimum here. We do have a low point compared to everything else. That happens at 4, negative 4. But there is no relative maximum for this one, right? So since this has an arrow and keeps going, it's not a high point. And up here, this is not considered to be a high point either because we have points that are equally as high right next to it. So there is no relative maximum. Now, looking at where we are increasing or decreasing, you want to put your lines through your turning points. It appears that we are constant on this interval, we are decreasing on this interval, and we increase on this interval. So looking at this, we are increasing from 4 to infinity, since it's going to keep increasing as it goes to the right. We are decreasing from 0, right, when x is equal to 0, all the way to when x is equal to 4. And then we are constant from negative infinity all the way to 0. The last part about this is, or actually second to last part, is that we want to now know about our zeros. Well, it looks like we have zeros happening right here and right here. Remember, your zeros happen where your function crosses the x-axis. So I will have zeros at 1, 0 and at 7, 0. And then for symmetry, this one does not or is not reflective across the y. That would definitely not work. And it does not have rotational symmetry, so we would say none. Let's take a look at another one. So here's a W looking guy that we kind of saw earlier a little bit. So again, as we drop this all down to look at our domain, we would see that all of this would fall from negative infinity to positive infinity. And when that happens, we just say that we get all real numbers. For your range, it looks like we will have a low point in our range that will happen at, let's just say that that happens at -5 all the way up to infinity. So that would be our range from -5 all the way to infinity. For our relative maximums and minimums, so our relative maximums, I'm going to try to do this in a different color. Looks like we have them occurring right here and right here. So at -2, 2, we will have 1, and then at 2, 2, we will have another 1. For your relative minimums, looks like we have low points here, here, and here. So looking at those, -5, -5, 0, 0, and at 5, -5 would be the location of those points. Now, in terms of increasing and decreasing, that's where it's helpful to draw your little light lines through your relative maxes and mins. It looks like we are decreasing from left to right over here, and then we go to increasing, then we switch to decreasing, then we switch to increasing, then we go to decreasing, and then we go to increasing, right? Remember, that's always read from left to right. So is the function going up or down from left to right in each of those sections? So it looks like we are decreasing from negative infinity all the way over till when x is equal to a -5. And then we start to increase from -5 all the way to -2. And then we switch to decreasing, right? So I'm going to just maybe put little check marks along. We've done this one, we've done this one, now we are working on this one. So we switch back to decreasing from -2 all the way to 0. And now we're going to be working on this increasing one over there. So we are then increasing from 0 to 2. And then we'll switch back to a decreasing from 2 all the way to 5. And finally, we will end up increasing from, looks like 5 all the way to infinity. Now, on a graph like this, what I would suggest looking at is just checking at how many spots you should be increasing and decreasing. So it looks like we had 3 decreasings, and we did have 3 decreasing intervals here. And similar to the increasings, we had 3 of those as well. So again, we see 3 of those over there. Now, our graph was not constant at any point here, so we will say this was no. And in terms of zeros, this thing had a few of them. We had a 0 that would happen here, 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 and here. So let me maybe even change those colors, give you something else to look at. So how about in this green color? So we had a 0 that happened here, 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 and here. So the locations of those zeros, let's just call this one, how about like 6.3, -6.3. Looks like we had another 0 that happened at maybe like -3.1. Then we, of course, had the 0 that happened at 0, 0. Looks like we had another one that happened at maybe +3.10. What am I thinking? Hold on. positive 3.10. And then it looks like our last zero maybe occurred up here at 6.3 again. So 6.30. Now, looking at this thing, this is the first graph we've seen that actually does have some symmetry, because if we were to fold it across this line, it would in fact hit. Now remember, if it folds across the line and hits, we say that it has even symmetry. Looks like we got just a couple more, so going through on this next one. This graph, we can see we got a couple of unique things. So we do have asymptotes happening right here. So we're going to get very close to these lines, but we will never actually touch those lines. So looking at our domain when it falls down will fall somewhere between here, and it will fall somewhere between here. So our domain will go from negative infinity all the way up to, it looks like that comes through at 0, all the way to 0, but we won't actually touch 0, and then we will go from 0 all the way to positive infinity. We can say this a couple of different ways. We can say, actually, kind of just as we have it written on the bottom, negative infinity to 0, union from 0 to infinity. Or we could also say all real numbers with x not equal to 0, right? So that just means everything except that one point. That might be a little bit easier way to write it. Looking at the range is going to be very similar to that. So when everything gets pushed over to the side here, again, we will kind of have an open spot that's going to happen at 0 there, just like we did on the other side. So we could say this again. This is going to be all real numbers with y not equal to 0. This time we say y because range is obviously your y values. Now looking at our graph officially does not have a relative maximum or minimum. There's no spot where we are going to switch from decreasing to increasing. So both of these would be nada. Another way of saying no. Looking at where our graph is increasing, so it looks like from left to right, this guy is going to be going down, and from left to right, this guy goes down. So there's no spots where we were going up, so we will say nope. Looking at our decreasing sections, it looks like we were decreasing from negative infinity now, right? So that's what we were just saying. So we were decreasing from negative infinity all the way up to 0. And then we are also decreasing from the other side of that 0 all the way to infinity. Right? This one gets a little weird though, because we're never actually at 0. Now, at no point does our graph stay flat. And at no point do we have zeros. Now, thinking about symmetry though, if I were to take this piece and rotate it, it actually would rotate on to that other part, right? So if this were to actually rotate down, it would land on there, so we would actually be able to say that this has odd symmetry. Last part about this. Our last problem would be this line segment over here. So looking at this line segment, so first we want to identify the domain. It does look like we get endpoints up here. So we will have a domain that will fall from -3 to +2. And it looks like our range will span from -5 to +5. It looks like our graph is strictly increasing, right? It's only going uphill from left to right. So it does increase on the entire domain from -3 to 2. Since there is no decreasing, we will say none. There was no spot where it was constant, so we can say none. In terms of zeros, it does look like we have a 0 that happens right there. So that looks like we're maybe at a negative 0.5. So negative 0.5, 0 would be the location of that 0. And then for symmetry, so looking at this thing for symmetry, if I actually were to rotate this down, where this would land, it actually would land right here and follow this. So it doesn't land cleanly on it, right, because it is rotating about 0. So since it doesn't land clearly on, we would say that this does not have symmetry, so none. Now, one part we didn't talk about on this one was relative mins and maxes, which are kind of important, so let's just jot those down for a second. On the surface, it looks like there are no relative mins or maxes, but since we do have endpoints on each end here, that actually is enough to say that that is the highest point in that region or relative to the rest of the graph. So we would be able to say that we would have a relative minimum at -3, -5, and we will have a relative maximum at 2, 5. Thank you guys for taking the time to watch this. I hope you found it worthwhile. Again, if you have questions, please either save them for class or make sure you're reaching out to me and asking. Thanks again. Have a great day.